Okay, section 1.2, computer realization and packaging. This is part of a book I wrote with Garbini and Devine on Picone. Computer realization and packaging. Recall the 5 primary components of a computer: the processor control unit, the processor data path, the memory, the input, and the output. Okay, in this section, we're going to see how these components are realized in hardware. Okay, different methods of packaging and connecting them are also going to be considered. So, realizing components in hardware. Let's look at processors first. Processors as integrated circuits. Integrated circuits are built with semiconductor material like silicon, and they're doped to create tiny circuits and circuit components like transistors primarily, encased in insulating material with conductive pins for circuit connections. Integrated circuits can have multiple functions. For example, you can have an integrated circuit that is an analog to digital converter or one for power regulation, but we call one a processor if it functions as a processor. We often refer to these as chips or microchips. Multi-core. So one chip can contain multiple processors. And in fact, most of the time nowadays, there are multiple cores in each processor. In this course, often implicitly, processor is referring to a functional unit, whereas processor chip or microprocessor refers to the physical integrated circuit, or IC. Okay, that was realizing processors. Realizing memory. Memory qualities, in addition to the ones we've looked at already: speed, capacity, volatility, and cost. Memory is also characterized by its rewrite ability. Read-only memory cannot be written to by the processor, so we can't write to read-only memory. And read-write or random access memory, RAM, can be written to and read from. Types of read-only memory, types of ROM. There's masked ROM, programmed during manufacturing, and can never be changed after that. Programmable ROM, or PROM, can be programmed once, and then it can't be altered again. And there's erasable programmable ROM, or EPROM, which can be erased and reprogrammed with UV light, like 100 times. Not a lot, and reprogramming with UV light isn't particularly convenient, so they're used for applications where we don't need to rewrite very often, but we'll need to a few times. Electrically erasable programmable ROM, EEPROM, can be erased and reprogrammed electrically or electronically. Flash memory can be erased and reprogrammed, but has a shorter lifespan than regular EEPROM. Notice that this erasable reprogrammable aspect of ROM is getting out of this read-only business. So we are blurring the lines as we get down here with the concept of ROM. Okay, types of RAM. Dynamic RAM, DRAM, requires periodic refreshing and is often used as main memory, which is where the program gets loaded into, where the data gets loaded into when our program is running. Static RAM, or SRAM, is faster and more expensive than DRAM, doesn't require the refreshing. It's often used for processor caches, which is a type of memory that's very close to the processor and accessible to the processor, and registers as well, which are very tightly integrated with the operations of the processor. So, secondary memory, solid state drives, SSDs, use flash memory, and hard disk drives HDDs use electromechanical components. They're usually a little slower, and they still keep hanging on though. We always predict the end of hard disk drives, and then they still seem to have value year after year. So input and output, how do you physically realize them? System bus, and bus is something that is supposed to evoke transportation. Okay, so system bus handles communication between processor and memory and the input and output. It's realized via conductors on a printed circuit board or on PCBs for compact and practical connections. So printed circuit boards are used extensively as the system bus. Peripheral buses. Devices connect to the system via peripheral buses. Examples of standards for peripheral buses are USB and SATA for storage devices. USB, of course, we're familiar with from a lot of peripheral devices that will plug into computers like printers and webcams and that type of thing. And SATA is more for storage devices like hard disk drives, like a backup drive, for instance. So we haven't really talked about standards much yet, and we will more as we continue, but a standard includes specifications for protocols, power, cables, and connectors. And we're going to talk more about peripheral buses and communication between the system and peripherals in the coming chapters. Specifically chapter 3, we're going to get into a lot of detail. So that's input and output realization. Packaging. Okay, so packaging. Motherboard, printed circuit boards, motherboard, PCBs. Copper layers adhered to an insulating base are what printed circuit boards are made of. And I'll hold up the UI board. This is a PCB, characteristically green in color, but you can of course have lots of different colors of printed circuit board, and the UI board comes in different colors as well. But there are traces of copper if you look closely at it on the back, and those are the electrical connections. And then the green is an insulator that is not electrically conductive. Okay, components are mounted using solder, ensuring both electrical and mechanical connections. Sometimes we overlook the mechanical connection aspect, but it's very important, as mechanical engineers like to think. Component mounting methods. So there are two common mounting methods for components onto printed circuit boards. There's the through-hole mounting. So components have wire-like pins or leads inserted into holes on the board. Holes are filled with solder for connection. Commonly uses dual inline packaging dip standard with pins extending in two parallel rows. So looking at the figure, let's draw our attention to this resistor here. This is a classic through-hole mounted resistor. We see these leads, and we would often trim off a large part of the lead and then solder each end to the board. So maybe here and here, solder to a printed circuit board. There is another through-hole mounted component here, which is actually a chip that's in a dual inline packaging dip configuration. So these pins here will poke through the board and will get soldered as well. So that's another type of packaging that's common, and mounting method that's common. Surface mount technology. In this, or SMT, in this standard, components have flat metal pads matched to copper pads on the PCB. Solder connects the pads during heating. used in modern electronics due to smaller size and suitability for automated assembly. So we have two SMT components here. This one, smaller one here, is a resistor. See how much smaller that is than this large through-hole resistor. And it's difficult to see because it's very small in this figure, but there are two pads on the exterior edges, here and here, that will take solder and will be soldered to the board. And then we have a chip here with SMT mounting, and these little pads here will get connected, will get soldered to the board. So two different types. The surface mount technology is more modern and is used for large production runs where we have automated soldering happening. And then through-hole components are easier for manual soldering and ideal for prototyping. Dealing with SMT manually is very challenging, if not impossible in some cases, whereas through-hole is something that you can do by hand. So depends on what you're doing. If you have a prototype, you probably want to work with the through-hole mounting, and if you're doing a large production run, you're going to want to move to SMT. Okay, packaging variations. So here are three types of packaging that we're going to be talking about off and on throughout the course. A microcontroller is a compact computer built into a single chip, so a single integrated circuit. It includes a processor, ROM, RAM, and other basic I/O support. It requires a circuit board for peripheral connections. So you have to mount this chip onto a circuit board to connect it to any other devices. It's primarily used in embedded systems, often low-cost devices as well. And embedded systems are ones in which the computer is a part of the system. Okay, so the computer goes along with it. It moves with the device. If the device moves, it's built into the device. So then the computer is embedded in the overall device or product. It is an embedded computer. So a lot of embedded computers have microcontrollers or are microcontrollers. There's also a closely related concept of a system on a chip, or SoC. Similar to a microcontroller, but with broader peripheral support. It includes interfaces for graphical processing units, GPUs, wireless protocols, etc., often used in embedded systems as well. And some SoCs integrate FPGAs for programmable circuit functionality, high-performance I/O, or digital circuit prototyping. For instance, the Xilinx FPGA system on a chip that we have includes the FPGA and a microprocessor as well. Good. A single board computer is a complete computer on a single circuit board. Can use a microcontroller, SoC, or a standalone processor in general, but typically refers to systems with microcontrollers or SoCs. An example would be the Raspberry Pi, and our MyRio board as well is a single board computer. We're going to exclude the term for traditional PCs with standalone processors. So a single board computer is one that has either an SoC or a microcontroller on it and functions as a standalone computer on one circuit board. So that's our single board computer definition. Okay, and finally, the target computer architecture that we're using in this course. So the MyRio architecture, it has this SoC, the system on a chip, the Xilinx Z7010 with a dual core Cortex A9 CPU. So this is the ARM v7A instruction set architecture chip. It has the ARM architecture, but concepts discussed here broadly apply to other ISAs. It applies to other ARM chips, but also many of the concepts we'll discuss will also apply to x86 processors as well. Integrated FPGA on the RSoC, so it routes most of the input-output through the FPGA for faster performance than a general purpose processor would give us. Common in high-performance real-time computers, but it's rare in low-cost ones. So you won't find this in Raspberry Pi, for instance, and you won't find this in an Arduino, except there are actually some variants of the Arduino that now include an FPGA, but they're still pretty rare. I/O interfaces. So the board, the myRIO board, comes with A and B connectors that have analog and digital input and output, and power outputs as well. And then a C connector, which is similar to A and B, but includes differential analog I/O and additional power outputs. And it also has a USB connector. So here is the C connector over here. And then we have the A connector and the B connector. And then, of course, the USB for programming. Good. And the target system connects the UI, electromechanical, prototyping subsystems, all to the target computer, the single board myRIO computer. And that's what we're going to be programming as we proceed. So, all right. We'll see you next time.